Right. Continuing the adaptation story, we talked about the warm water species and cold water species and their general features, especially for the plankton, which don't swim too far or just drift along with the currents. The other adaptation is required, as I said, is related to getting rid of the body waste and taking in nutrients. So they need to have high surface area to volume ratio to optimize the buoyancy part and this nutrient waste exchange part. So we can understand it's better by looking at just a cube for simplicity. Let's assume it's a crab larvae that has a cubic shape of side 1. The surface area then is obviously 6 times this. It's six times each side, 6 squares, right? And volume is related to the side cubed, so it's 1. So surface area is 6 and volume is 1. S over V, surface area to volume ratio becomes 6 over 1, and that's 6. So if you think about oxygen diffuse across the skin, almost all of the oxygen here can be accomplished easily by this high surface area compared to the volume. Now let's say we take a amphipod, which is a bigger cube with the side of 2. So you now have square of area of 2 squared times 6 faces, so you have a surface area of 24. Very simple. And the volume is of course 2 to the power of 3, 2 cubed, which is 8. Now the surface area to volume drops all the way down to 3. So it's went from 6 here down to 3. So now the diffusion across the skin on this larger cube with much lower surface area compared to the volume is 40%. Just some measure of diffusion across the skin given the surface area to the volume. Okay, take a box crab which is got a, let's say fits into a cube of a side 4. Then you are changing the surface area to 96 and the volume goes up to 64, and the surface area to volume ratio drops to 1.5. Okay, we went from 6 to 3 to 1.5, and now here you have oxygen diffusion across the skin of only 5%. Right? So you have the marine life has to optimize the surface area to volume to optimize its buoyancy and use of viscosity to the need for oxygen and nutrients and waste disposal and so on. So they end up developing these kind of unusual appendages to increase the surface area. So here is a diatom that has a huge body in the middle and a surface area increasing appendage that provides it much larger surface area, right? So many of these microorganisms also have either a gas chamber where they can take in dissolved gases and increase buoyancy and get rid of it and decrease buoyancy, or they produce drops of oil on these kind of surfaces, many microorganisms. You think these are microorganisms, so you literally need a microscope to look at them, but over millions of years, these little tiny droplets of oil can accumulate and produce oil deposits in the ocean, in the sediment of the ocean, right? So the fossil fuel we are burning is basically a hydrocarbon that's generated like this over millions of years. Millions of years. Continents have moved, glaciation, deglaciation, ocean has risen and fallen and so on. Life has photosynthesized and produced these kind of oil droplets over millions of years that has been buried, that we are now digging up and burning and converting to carbon dioxide and nitrous oxide, methane, and other pollutants like mercury and so on and so forth, right? So all the fossil fuel is of biologic origin, and it could be related directly to buried hydrocarbons, photosynthesized material that became charcoal, peatlands, and natural gas and crude oil, and so on and so forth, right? So biology gives us all this energy in fossil fuel form, and if you think about it, that's essentially solar energy, because they are all capturing energy from the sun with photosynthesis or other forms to convert to fossil fuels. So other than tidal energy, which is mostly coming from the moon, and geothermal vents, which is coming from the mantle, and so on, we are mostly relying on solar energy in various forms. Wind is because of solar, waves are because of solar energy, and so on and so forth.